Hi, in this lecture I'm going to talk about two ways we can geometrically understand systems of linear equations. There's no counterpart for this in the deep learning textbook that this course goes with, but this will make the next lecture where we talk about linear independence and span a lot easier to understand. So let's just start off with an example. So we already learned what systems of linear equations were a couple lectures ago. Basically, let's give an example here. So let's say I'm going to color coordinate because it'll make things a lot easier down the line. So let's say 2x plus y equals 3, and let's make a second equation here. X plus y equals 2. So this is a two-variable system of equations, and it's solvable, and it's pretty easy to solve just by looking at the equations. We don't have to do that much. We can kind of clearly see that x equals 1 and y equals 1, and you can convince yourself that that's true. And as we learned before, we can represent this as a matrix equation. So let's do that quickly. So ax equals b form. So let's create our coefficient matrix A first. So that's going to be 2, 1, 1, 1, 2, 1, 1, 1. And then next up our variables vector, x and y. And then equals, this is the right-hand side here, 3, and 2. Okay, great. So that's our ax. We already wrote that. All right, so there's my eraser. Okay, great. So there's two different ways we can understand this. So the row picture and the column picture. And these terms come from, I'm not sure who first thought of them, but they were kind of popularized by Professor Gilbert Strang at MIT, whose linear algebra lectures are often used by people who are learning linear algebra for the first time. So I kind of took it from that. But let's look at the row picture first. And it'll make sense why it's called the row picture shortly, but it's probably the one that you're already familiar with, just not under this name. So let's draw a Cartesian plane here. Okay, and let's label it. So let's say 1, that's about 1, it's not perfect. The reason why I want to make this as perfect as possible is it'll be important later. 2, 2, 3, 3. Okay, that's good enough. So now let's draw out these two lines, because these obviously are the equations for two lines because they're linear. And I already calculated the x and y intercepts because I didn't want to take more time. So let's look at this first. Let's graph this first line here. And the y-intercept of this is 3. And the x-intercept is 1.5. So that goes from here down to about here. So let's try to draw that to the best of our ability. That's pretty good. I'll take it. And now we want to draw this one, which has an x-intercept of 2 and a y-intercept of 2. So that goes from here to here. And that goes from about like that, pretty much. Okay, so those are our two lines. And you probably already know this understanding that the intersection between those two lines, so this little point here, represents the solution to both of those equations because that represents the value of x and the value of y. That satisfies both of the lines, and that means both of the equations. And you can see that's pretty much correct. So we can see that equals 1 and that equals 1, so that's our answer there. So that's what we call the row picture. And the reason why is that if you're looking at this matrix here, this matrix equation here, these equations, 2x plus y equals 3, kind of can be read as the rows of this, 2x plus 1y equals 3, and then 1x plus 1y equals 2, sort of can be seen as the rows of this. But it'll become clearer why it's called the row picture when you look at the next one, which is the column picture. So the column picture is the one that you might not be familiar with. So just for the first part, you just have to take my word on it, and then it'll make sense later. So what we're going to do is we're going to basically represent this as a vector equation. That's the whole point. So what is the equivalent vector equation for these two linear equations here? Well, let's take this column here, the first column of our coefficients matrix, so 2 and 1, and make that into a vector. So I'm going to do stuff up here now. So 2 and 1. There we go. So that's our first vector, and that's the first column of this. And let's multiply that entire vector by x, so our first variable. Okay, now let's add this to our second vector, which you guessed it is the second column of our matrix. So this is going to be 1 and 1. Great. And then we're going to multiply that by our second variable, y. And this is going to equal our right-hand side vector 3, 2. Okay, great. So that's our vector equation that represents the same linear system of equations, and it'll become clear why these things are equivalent just in a second. So let's now create another Cartesian plane and plot these vectors on it, these three vectors. So 2, 1, 1, 1, and 3, 2. Let's plot those three vectors. So let's create our Cartesian coordinate plane. So it's going to be of similar accuracy as the other one. 2, 2, 3, 3. All right, so that's our Cartesian coordinate plane again. And now let's plot these three vectors. So this red vector here, 2, 1, is going to be x equals 2, y equals 1. So it's going to be around here. Let's plot the arrow with that as well. And then now let's plot our second one, which is 1, 1. So it's going to be here. So let's plot that like so. And then finally, let's plot our 3, 2 vector. So x equals 3, y equals 2. So it's going to be about, let's eyeball it about here. And now let's draw that as a dotted, black dotted line. Okay. So I'll show you in a second why these are equivalent. But first we've got to talk about very quickly how we add and multiply vectors and how we can understand that geometrically. Of course, this should all be reviewed, but it's also good to review this as well. So multiplying vectors. So if we have some vector here that we represent geometrically, you have some vector here, and we multiply this vector by 2, that's basically equivalent to just making the length of this vector 2 times the original length. So that'd be equivalent to just kind of putting one more of these vectors on top of each other, and now this new vector here is going to be twice the size of this original one, but the direction stays the same. So that's how you multiply vectors. So if you multiply this by 3, then you get a vector that's 3 times the size of the original one, etc. Additionally, how you add matrices, so if you add vectors, if you have a vector like that and you have a vector like that, geometrically adding vectors, well, of course, adding vectors, we already talked about, is quite easy. If you have like some 2, 1 plus, say, 3, 2, you just add the elements to each other, so that would be 5 and 3. But geometrically, we can understand this to look like basically taking this first vector here and taking the second vector here. If we want to add this vector to this vector, we just think of it, we call it kind of heads to tails addition. So we take this and we put this to the head of the other vector, and then we start the tail here. And just basically move that, imagine moving that whole thing to the head of this vector, and then our new vector is going to be basically the distance from the tail of this to the head of this. So I won't prove that that works, and I won't prove that that's equivalent to the thing I just showed over here, but it is, and you should be familiar with this already. So that's basically how you add them, that's how you multiply them. So now let's do the same thing, but here with the vectors that we're concerned about. So let's just assume that x and y are the answers and plug those in for x and y there and see that it satisfies this equation as well. So basically, it's pretty easy. We have x and y, so that means we don't stretch any of these vectors individually. If this x was equal to 2, that means we'd have to stretch this vector 2 times the size of what it is already, so that would be 4 and 2, but we don't, so we just keep it here. And this blue vector here, we also, since y is also equal to 1, we just keep it steady as well. And now we add these two. So we add them just like we did here, heads to tails. So let's imagine taking this vector here and kind of dragging it to the top of this vector here. So let's do that. 1, and then drag that to there. That's about it, right? It's about the same vector. So our new added vector, we'll see, is equivalent to our answers vector 3, 2. And that's kind of the picture here. And, back here we were solving for the coordinates of a point that represented the intersection between two lines. And here we're looking for the proper values of x and y to multiply our columns of our matrix A by, or the vectors of matrix A by, to perfectly get to the point represented by the answers here. So here we're looking for x and y that are scalars, and here we're looking for x and y that represents an intersection between two lines. But they both give you the exact same answer. Here the right answer is x and y, which allow you to get the exact same vector 3, 2, and here the answer is also 1 and 1 because that represents the intersection between two lines. So that's kind of the two ways of viewing geometrically what a system of linear equations is. So hopefully this will make the next lecture a lot easier to cover. All right, I'll see you in the next lecture. Bye.